Afternoon, everybody. My name is Carlo Cavazzoni. I'm actually in the ecosystem of HPC since many years. Probably most of you know me because I was for many years in Cineca. Now, starting from the 2020, I'm in Leonardo, which is a large, let's say, Italian enterprise, but actually we are, let's say, our business extend well beyond the Italian border. And in Leonardo, I'm responsible for the HPC and cloud infrastructure to serve the internal engineering, most of all internal engineering. So just a few words about Leonardo. So Leonardo, many of you probably know Leonardo with its previous name that was Finmeccanica. Now actually the name of the company changed, and but the business remain almost the same. So we are active in aerospace and defense business, where we let's say our product are helicopter, aircraft, but defense electronics and space application, and also cyber and security solutions. Let me try to switch. So just few figures about Leonardo. We are, let's say, I missed, no, the next one. So as I said, we are an international company. Our business volume is more or less in the order of 14 billion euro. At least this was the 2021 figures. And we spend, this is an interesting figures for you. We spend 1.7 roughly billion of euro in R&D in the company. We are almost 50,000 people. And as I said, we have office all over the world, but mainly in Italy, UK, US, and Poland. These we consider our domestic markets, where we have engineers and also production plant. Since 2020, when I arrived, Leonardo decided that in order to boost the technology evolution toward a more digital future, and in particular following by strategic 2030 innovation plan to, let's say, at the corporate level, give rise to new R&D unit that can, let's say, support the engineering and engineers of the company with, let's say, transversal service. And this is especially true for the technology we are talking about today. So digital, essentially connected to digital transformation. And if you want more in detail, HPC simulation, because many of the problem that connected to the simulation that an aircraft engineers face every day are similar to the problem an helicopter engineer faces, or for the engineer that is designing space or electronics devices, no? And so these labs have the mission of technology incubator and to support, as I said, the long-term vision and the technology transfer between the technology innovation and the actual technology used in everyday business. So today, the structure of the labs is the following. So the Leonardo Lab, we have more or less 11 active lab, The main labs are located in Genova, where is the Da Vinci one and my own unit, but we have also labs in many other regions of Italy, and also one labs in US, where let's say co-located in one of our subsidiary company, which is Leonardo DRS, which is a large company in US. Today we have more or less 80 researchers, but we plan to increase the number of research fellow by the end of 2022 to more or less 130 researchers. So we just open a new call for proposal, so people can submit their candidature to be part of the Leonardo Lab, and then we will start a selection process among the submission we received. The basic infrastructure of the Leonardo Lab is our supercomputer, so which is used by all the Leonardo Lab. When we install this, so the supercomputer, which is called Da Vinci 1, and has more or less the computational power of 5 petaflops. And when we install it, it was well within the first 100. It was 80 something in the top 500. Now that 2 years are passed, more or less 2 years, the ranking is not so bad. Is not so bad because it's in the top 500 right now. It's 136. So it's not a tier 0 system. Is more or less a tier 1 system. But for a company, it's not so bad. If you take the corporate supercomputer, is in around the position number 20 today. When we installed it, it was the 10th corporate supercomputer of the world. But as you know, in the top 500, the systems can lose position quite quickly with the time. So we have planned to replace it in 2024. So this is the process of maintaining the infrastructure will be similar to what will be a tier 1 let's say research system for not only corporate but also let's say national lab. So so in the same the interesting thing is that we have in the lab, along with the supercomputer, we have also big data, a big data infrastructure, which is, I will explain in a minute, which is supported by an internal cloud, which run actually on the HPC as well. So we have in the same infrastructure 2 essential services. So batch, let's say the usual batch system and a cloud-like infrastructure. And we also have the people developing application and software. So for what concern the current speech, so interested for you probably, there is the concept we develop about the digital twin we are, let's say, implementing within the company. So the lab, as I said, the lab support, so the Da Vinci one support all the labs. So among the labs, there are also lab looking at electrification of the fly, look at the new materials, so light materials, looking at, let's say, using of quantum technology. We also have within our lab quantum computing initiative, but also quantum communication and quantum technology in general. But one of the central topics and let's say research topic, yes, we are dealing with is the one connected with digital twin. For us, digital twin is, first of all, a multi-component, multi-scale system, a digital system that should support the virtual design and lifetime management. So, it's a comprehensive, complex object that is based on two main technology stack, so software stack essentially, but in general technology stack. One that support a model-based digital twin, and the other that support data-driven digital twin. And the two have to speak together, so to work in synergy among themselves. So the model-based branch, if you want, of the digital twin, obviously is the one which is more closely related to traditional HPC, because here we have numerical models. So we are investigating the evolution of numerical models, and then we use HPC to perform simulation, and like CFD simulation for the engineering of our own products. On the other side, instead, there is the data-driven digital twin, where the need is to collect the data from the field, so from the sensor actually installed on test beds or prototype of our platform, and then use data lakes, so cloud-like technologies rather than HPC, to build the data lakes and to allow the data scientists to build their workflows and allow at the end to deploy even artificial intelligence kind of application. And both simulation and artificial intelligence at the end try to make or support the engineers with predictive models. From the point of view of simulation, the model is explicit, so we know the equation, we know the numerical model, a different level of complexity, obviously, and we integrate an equation in order to make a prediction of a behavior, a pressure, temperature, the resistance, and so on and so forth. With AI, the idea is to make prediction as well, but with implicit model. So we train algorithm to make an example for predictive maintenance. So we train the neural network based on the data we collect on the data lakes in order to build a predictive model to support the maintenance in the operation of the helicopter or the aircraft or other tool. For us, more data and compute capacity means more accurate prediction. This is the end game of this loop, no? And this is motivate the fact that we invest in HPC resources and cloud-like resources. When I say cloud, I'm not referring to a public cloud, but at an internal cloud. I will show you shortly. Around the digital twin, there are many other, let's say, ancillary topics or goal, like the digital design, the multi-objective optimization, predictive maintenance, as I said, but also important for reducing the cost of designing, let's say, a helicopter or aircraft, like certification by simulation. So to be accurate, such that we can perform a part of the certification process of one of our products, just performing simulation and not actually building a test bed, a real test bed, and to crash it or to to let's say, certify going through a test campaign. So as I said, the two paradigms, so the model-driven and the data-driven, are supported by two different software stack. Okay, from the model-based kind of digital twin or simulation, we use a traditional HPC software stack down to the let's say software paradigm for accelerator, compilers, debuggers, and MPIs, batch scheduler, parallel file system, and all what you find in any other HPC system around the world. But for the data-driven digital twin, we need a different ecosystem, also because the skill of the people working on this kind of environment are different, and we need to build a standard, let's say, software stack for this kind of application, so which is naturally being deployed and evolved on cloud-like infrastructure and tools that in most cases come from the Apache ecosystem plus Python, let's say. So it's a different kind of ecosystem, and the people naturally use the browser as an interface to their developing environment rather than an SSH or a terminal. So for this reason, we support, just to make, as I said, the typical traditional HPC simulation software stack and the machine learning and deep learning software stack. As we do that, so we try to share as much as possible of the infrastructure, but for sure there are two key things and two key infrastructure component that allow to do that. And one is the network. So we have two main backbone, one InfiniBand backbone in the machine and 100 gigabit network connecting all the nodes of the machine. So we have essentially two backbone, and we have two different storage systems. So one is a traditional POSIX lastre file system, and then we also have a cloud-like Ceph storage infrastructure. We have on the compute node are shared between the two systems, so user can access the bare metal infrastructure using SSH, or on the other side they can ask for a tenants to develop so a virtual set of virtual machine where they can deploy their let's say workflow, big data workflow. So let's then come instead to speaking more in detail what is the roadmap toward Exascale. So the main problem is connected to the model-based digital twin. So the possibility to have larger simulation, more accurate simulation, and coupling different technologies. So when we would like ideally to be able to perform fluidostructural simulation of an entire complete helicopter, just to make an example. And to do that, actually, one of the limits we have today in the company quite often is due to third-party codes. So either because maybe those codes do not exploit efficiently new hardware like GPUs, or either because the cost of license is too high. So the idea is to, let's say, to look forward for, let's say, alternative technology, mainly coming from the open source world, so community code, without, let's say, abandoning the third-party code that for us remain anyhow an important asset. We spend many different tens of millions of euro in license every year, but obviously the limit is that this license do not scale. The licensing model does not scale to not even to petaflops kind of infrastructures. So these are a few topics we are investigating. So and we are also looking for new numerical technology like lattice Boltzmann or multi-grid techniques in order to let's say overcome the problems we are encountering today using a third-party or legacy software stack. Consider also that an important goal for our engineer is the time to solution, so they cannot wait months to get the result. Ideally, they would like to get a result, so a computation complete within 1 day. So this is the target they are seeking, just because they would like to keep the iteration cycle between the computational engineer and let's say the engineers dealing with the real design of the whole the structural and system engineers. They would like to keep this loop quite short and to be able to shorten the design cycle of the platform. So so our tool chain to EXCELLERAT, so hexa or whatever scale is above petascale. As I said, now we have our machine is only 5 petaflops, but for us it's already challenging to scale to the whole machine. Also because for this kind of problem, the codes or many third-party code does not scale, in particular for our use cases. So our tool chain we are validating and testing right now is to use, let's say, a CAD tool, which is in the end of the system engineers, which is based on basically on all the company they use CATIA. So the idea is to, let's say, from CATIA use another tool, which is in this time pointwise, to convert let's say fix the problem with the grids and make the grid itself, the computational grid itself, open, meaning that we can play with it as we can, as we would like, in terms of porting the model to different tools and open source tools. And the two tools we are investigating right now are OpenFOAM for, let's say, CPU-based simulation, and PyFR for GPU-based simulation. So we are benchmarking some, let's say, tests from the literature, like this one. As you can see, we are performing different tests at different scale of accuracy in terms to see what are the difference between and the advantages using higher order kind of simulation. But the goal is to use and simulate object of this scale, where the grid is composed by billions of elements. I think we are not such far from that. I think before the end of the year we will be able to actually let's say get a try to have the first run of a complete grid representing an helicopter. We are spending a lot of time fixing the grids because this will, as you may know, have an important impact in the convergence property of the simulation. So if in the grid there are holes or there are submicrometric refinement, these are not, let's say, going to work with convergence time. We would like to be as quick as possible. So these are a few preliminary results the researcher of the lab are obtained on test system. So we are doing weak scaling with PyFR and strong scaling using GPU, because one of the target is to enable the use of GPUs for engineers. So as you can see in the top panel, there is the weak scaling for two different, I think, two different, let's say, numerical schemes. And obviously, as you go higher with the order, the number, the weak scaling can be better. And in the lower panel, you can see the speed up in the strong scaling, which I have to say is not such bad, considering we started to play with this kind of code since a few months, but already we are able to reach scalability to a considerable number of GPU. So 128, our GPU are A100, so the latest NVIDIA GPUs. So 128 GPUs correspond to 1.5 petaflops of peak power, more or less. So we are already able to scale up to, let's say, 1 petaflop. So if you want, the journey to exascale is still quite long, but I think this could be only, let's say, reached combining different kind of simulation patterns. So we should combine, let's say, tightly coupled simulation for one system alone, together with ensemble-like simulation, where we are going to assess different geometry at the same time all together. So this will be the path how we can reach even in reasonable time also the need for exascale infrastructure. I think that's almost everything. Just last two slides. We are going to, so the researcher of the labs are going to present more results in detail at the following conference. You can see in the video, in these slides. And last but not least, these are the researchers that are, let's say, the engine, the brain power behind all this I have shown today to you. And that's it.
Thank you very much, Carlo. So I'm looking into the chat whether we probably have a time for one or two questions. So if you have a question, feel free to just post it into the chat. I stumbled across one of the words you mentioned. You have pretty tightly coupled HPC and data analytics in your system, and you said you have actually different file systems, and you mentioned the word data lake. And so data lake, actually, the idea of it is you have something big and you throw everything into it and then you use it later. Then I thought about what's the data lake in HPC. I think there's nothing like a data lake, but usually you hear SDM, so simulation data management. So have you thought about how the data lake and the data management in HPC, how they fit together? Is there something you see a need to do, or?
Yes, definitely. The HPC storage is let's say supported by two facilities. One is a work area of 2 petabytes, and one net space, and another one is 10 petabyte of available space, so net space for archive. Then we have a gateway to export the archive as S3 blobs. So in principle, it is possible for the data lakes built on tenants running on the cloud to import, if needed, S3 object from the archive. This is something obviously to be tested, and it is really an activity of research. So at low TRL is not yet in the hands of the engineers, but the goal is to close the loop. As I said, this is if you want, is the link between the data-driven model and the so the data-driven digital twin and the model-based digital twin, because one of the issues we are confronted often is so many years in the future or many years in the past. So an helicopter stay operational for 20, 30 years. So something happened to an helicopter after 20 years of operation. So the problem is that someone find a weakness in the structure, no? And there is the need to look back on what was the cause, no? Now, for what is currently flying, most of the documentation is paper-based because very few. So we have some digital stuff, but very preliminarily. And one of the challenges is also to preserve the tool chain, because after 20 years it's really difficult to have the same version of the software, the same version of. So the problem is now we are also looking at containerized technology. We run most of our application in containers, even in the HPC, to try to also package the application along with the data. So this is
well, I guess that's a big challenge that, especially I think in the aerospace industry, is probably even harder, but also automotive, I think they face the same thing. So thanks a lot, Carlo. That's been very interesting. And well, you won't be in Oslo, but I will be and chairing the session, so I'll hear more about your activities. So thanks a lot. And I'll switch now to our previous host, so to speak. Now as a speaker, Mark Sawyer from EPCC. I think in this context everyone knows him, so there's not much I need to introduce about you. And I'm looking forward what you will tell us about EXCELLERAT, the results, and the outlook for Exascale. Please, Mark.
Thank you very much, Andreas. Can you see my screen?
We see the speaker's view. Now it's fine. Perfect.
Now you see it. Okay. I've also gone 1, 2, 5. So it's wonderful when technology works. Hopefully, you see my title slide. Thank you for the introduction, Andreas, while I've just got myself set up to present. Yes, as Andreas says, I'm Mark Sawyer from EPCC, which is the HPC Centre at the University of Edinburgh. And it was my role within the EXCELLERAT project to manage one of the work packages that was looking at a set of reference codes and use cases around which the whole work of the project was built. So my talk is going to cover at a fairly high level the work that we did with those use cases, some of the results from it, and what the outlook could be for the future. The reasons for me treating it at high level are twofold. First, there isn't really time to do justice to the amount of technical work that's gone into all of into the project. And secondly, I'm not really a technical expert on any of the application code. So for that reason, it's going to remain at a high level. That if you are interested in more detail, there's a great wealth of publications, papers, presentations, success stories, and so on that have been produced by the partners. And we are in the stages of producing a final deliverable, which will be public, and that will be a good summary of all the results and all the work that we've done. I thought it would be worthwhile to start with a little bit of background about why we're motivated to do the project, what the methodology was, and a little bit about the organization, because that really does help in understanding our overall process of operating the project. So here's our mission. So the project was set up to establish this single point of access for expertise in all aspects of the engineering life cycle. So data management, analytics, simulation, visualization, and co-design with HPC. Why engineering? Well, it's an enormously important industry for Europe. There are over 100,000 companies directly involved in engineering. It's a 2 trillion euro market, and about a third of all exports from the EU are engineering related. So it's of enormous economic benefit to the European Union. So I mentioned the engineering work cycle. So here's a sort of simplified diagram of the whole engineering work cycle that we're talking about. So this treats simulation, post-processing and analysis of results, feeding back into pre-processing, and at each loop of this cycle, we're looking to improve some design aspect of an engineering problem. But of course, what we want to do is treat this in the context of real-world applications. What we're interested in here is how the codes and how this engineering work cycle performs on real computers. We're not trying to benchmark the performance of the computers themselves. It's benchmarking and performance analysis of the applications at each stage of this work cycle and the work cycle as a whole. Okay, so this is the only slide I'm going to put up that says anything about the project structure, but it is, I think, important to understand the way we went about things. So you'll see there is a sort of core of in the center there, which has 3 work packages. One is the application development, and that's the one I'm primarily talking about. But in fact, we had other work packages that were focusing on particular methodologies and technologies. So that's work package 3. So this is things like improving individual node performance, looking at system performance, other technologies like visualization, data handling, mesh generation. And then at the other work package in there, work package 4, was looking at how these could possibly be servitized in a way that would make the center sustainable through offering these to external parties through a service portal. And there's a lot of progress made in that area towards the center becoming, 1, sustainable, and 2, being able to offer its services to a much wider community. Okay, so to just list the codes that we have. So we have 6 codes. We've got NET 5000, ALIA, AVBP, TPLS, Phoenix, and Coda. And I'll be going through each of these to say a little bit about what they are and something about the use cases and the results that we got from the project. So this is a list of the use cases, and as I said, we wanted to root the project very much in real-world problems, real-world engineering problems. As you can see from this list, there's quite a strong focus on aerospace and automotive applications. That shouldn't really be a surprise. They're traditionally been consumers of high-performance computing and very demanding on compute resource and very challenging for simulation. And so that you could sort of regard those as being kind of the leaders, the areas in which technology tends to be furthest ahead in terms of the simulation and the optimization of code. So that's got a good starting point to take us forward towards Exascale. Okay, so I'm now going to go through each of the reference applications and say something about the use cases associated with them. So I've got maybe 3 or 4 slides associated with each one. So the first code I'm going to talk about is called NEC 5000. So this is, as it says on the slide, it's open source, high order spectral element method CFD code. It's been under development for quite a number of years. So there's a lot of legacy development has gone into this code. So what it does, it solves Navier-Stokes, incompressible Navier-Stokes. It does a lot of other types of physics as well. So there's heat transfer, there's electrostatics, and a number of the other things that I've listed on the slide. The EXCELLERAT partner that was involved in this code was our colleagues from KTH in Sweden. And they had two use cases associated with this code, which one was both from aerospace. One was flow around an aerofoil, static aerofoil, and the other one was a simulation of rotating parts. So here's some, as always with CFD, you get some nice colored images. So this is one that shows the aerofoil with the rounded wingtip. And the flow from the simplified rotor. If we look at why these are important simulations, because the researchers are interested in the results of these as well as the optimizations that we make and the improvements to the performance of the code. The actual results of these test cases is useful. In the case of the aerofoil, obviously, the lift and drag affect the performance of the aircraft, but it's not just simply the performance of the aircraft itself. There are safety margins that are required due to turbulence that is downstream from the aircraft as they take off and land. And so if that can be controlled, if that can be improved, then it means the industry itself can operate more efficiently. So there are benefits beyond simply to the individual design case here. Okay, so to talk about some of the things that were achieved by KTH and their colleagues. So one of the big things in this in these use cases was incorporating adaptive mesh refinement, and that allowed some previously unaffordable simulations to take place. So effectively, the idea is here to make the mesh much finer around the regions of interest and do this during the runtime of the simulation in response to the way the physics is developing. We heard earlier on today about the Ugit uncertainty quantification toolkit, so I won't say very much more about that. The simulations were tested at full scale on the Dardel and Lumi supercomputers, so Lumi, the pre-Exascale machine, and both those showed good, strong scaling. So there's optimism here that we have codes that can scale up to Exascale when those machines are in place. The integration of the visualization tools, again, that was something that was covered by Dennis in the earlier presentation. And as I said, the researchers were able to gain some real results on the turbulence stats and the other things that they needed to understand from those from the simulations. So if we're looking at what the sorts of things that the team are looking at next on this, trying to break down into several areas. So there's some to do with numerical improvements, so things like preconditioners and multi-grid. There's the actual implementation of some of the communication and computation kernels, and there are things like advancements to the meshing strategies to capture geometries better. And then looking at things like some data reduction techniques so that the post-processing becomes a little more efficient. And so you can see how these things will affect different parts of the cycle, the yellow cycle that I showed earlier on. Okay, I'll move on to the next code. So this code is called Alia. It's a multi-physics HPC code using the finite element method. It's very large scale, complex geometries. Unlike NEC 5000, this isn't open source. It's distributed according to a license use agreement, and it's the EXCELLERAT partner was our colleagues from Barcelona Supercomputing Center. And again, we had two use cases associated with this code. The first one was to do with emission prediction from simulating the combustion inside a gas turbine engine, and the second was a flow over an aircraft wing to analyze the synthetic jet actuators. So if we look at these, here's some, again, nice pictures showing this is the sort of use case that the team was looking at. So the work in here, the people at Barcelona did a huge amount of work on developing the fully parallel workflow. So this is trying to ensure that every part of that engineering work cycle is benefiting from parallel computing. So the bottlenecks that you would get by not improving the whole cycle are kind of removed. There was a lot of work done in this project on load balancing, both at node and system level. So as you could imagine with something like a combustion simulation, there's a lot of work concentrated in certain parts of the domain, and being able to redistribute the work at runtime is going to give you much better scaling. So yeah, developing and incorporating the adaptive load balancing was a big part of the project. As with some of the other codes, as you'll hear later, the porting to GPU and other emerging technologies such as FPGAs was quite a big part of this project. We all know that the next generation of computing, exascale computing, is going to incorporate technologies like GPUs and other accelerators. And so having codes that are ready to take advantage of those is going to be an important step. And so once again, this will let the project enabled real analysis of some of the results from these two use cases. So the researchers are actually interested in what was being simulated, had some useful outputs. That I've already said. So basically, yes, basically what the Alia team are looking at is to improve take the load balancing and take that all the way up to system level, and continue the work on the accelerators and GPUs. AVBP is the third code I'm going to talk about. So this is finite element, finite volume, 3D compressible flow solver. The EXCELLERAT partner for this is Surfax in France. It does a lot of it's kind of the general CFD things, large eddy simulation that can use unstructured grids. And once again, this is a license code. It's not open source, so it's distributed case by case basis for open science. The use cases here, one was a safety application. So this was an explosion in a confined space. And that's using a standard model geometry, which is kind of important for comparison of results. And in the aerospace and potentially in the energy sphere, looking at combustion instabilities and in emission predictions, so that aircraft engine, for example, can meet emission requirements. So if we look at this, we have on the right-hand side is the explosion in the confined space example, and on the left we see the aircraft engine. So what do we do? What was the work that was done in AVBP? Once again, there was a lot of work done on the adaptive mesh refinement. and adapting this and adapting the code for GPUs. One thing that the project achieved was this cross collaboration with the EPEC project, and this produced an adaptive mesh refinement tool called TreeAdapt, which was incorporated into AVBP. And this greatly improved the efficiency of the computation as a factor of 2 speed up compared to just having the static mesh. So that's a big step forward. And there was a very successful port to a GPU version, which was then run on a tier 1 Jeanzé system from Jeanzé. So a lot of progress there towards Exascale. The next things that AVBP they're going to be looking at is Lagrangian simulations, more automation of the workflow, looking more at the hardware acceleration and new technologies, and just further code maintenance. I'm going to mention now TPLS. So TPLS, that stands for two-phase level set. This is slightly different from some of the other codes because it focuses on quite a niche scenario, which is modeling the interface between multi-phase flows. So this is a very important thing in the chemical engineering industry, for example, because it deals with things like distillation, mixing of fluids, and those sorts of industrial processes. It's being developed by the University of Edinburgh and University College Dublin. It uses a mixture of PET-C and some handwritten solvers. I'll say a little bit more about that in a moment. And the use case that we had was a two-phase bidirectional flow, which looks something like this. It's not as colourful a picture as some of the other ones that we've seen, but basically what this is there's a countercurrent between the liquid, which is the kind of grey stuff at the back there, which is a falling film, and then there's a gas phase which is flowing as a countercurrent. And the thing of interest here is to model that interface between the liquid and the gas. Okay, so what do we get out of the project from the TPLS? So one of the things we did, we looked at the GPU performance, and we were quite surprised that this didn't perform very well on GPUs. And what we discovered was that the PET-C libraries were not very well optimized for the GPUs that we were using. There was some issue with the performance. So what we did was develop a native GPU version that we now have available to release into the main code. We did some stuff on I/O scalability, so we removed some bottlenecks and some requirements for some nodes requiring very large amounts of memory in order to be able to run the simulations. So that has increased the ability of the code to scale. Added some new phenomena to this. So a new method for identifying the interface between the fluids was developed. So that was to enable other physical phenomena to be modeled, and we've also added some temperature and introduced the proportion of vapor in the gas phase as degrees of freedom. So quite a lot of extra physics going on in this in TPLS as a result of EXCELLERAT. In terms of its performance, we've demonstrated very good parallel efficiency, and that's up to over 30,000 cores. This is a CPU version of the code, but the results we've achieved so far seem to indicate that it will scale well beyond that, which is interesting. I'll move on to what the outlook would be. As we reach the point where the strong scaling ceases and we start to be more weak scaling, what we can do is introduce some more, that's an opportunity to introduce some more physics into this to sort of increase the load and exploit the weak scaling. So that's probably the way things will go forward. We still have the GPU enabled code ready to use when we have access to such a machine, but we do understand that I think the PETC code is going to be has had a lot of work done on the GPUs, and consequently that may in fact be the best way to use the code of GPUs rather than the native version, but we still have that available, and of course that means the code is more portable. Phoenix. Okay, Phoenix is a little different from the other codes as well. It's more of a problem-solving environment which generates code from a more sort of mathematical description of the project rather than a programmer directly coding things. So so in that sense, it's more of a problem-solving framework. The work that we did mostly in EXCELLERAT was to do with the adaptive mesh refinement and looking at some of the components that plug into the framework. So the EXCELLERAT user partner here were Chinica and KZH, and the use case here was at a joint optimization using of a car shape, which I just got a picture of here. So this is a standard model that's used for benchmarking this kind of code. So that's useful for comparison with other work. So what we did under Phoenix was we did some advancements in the mesh generation. It was mainly around the mesh generation refinement, and we tested it using a standard geometry. There was a particular problem to be solved of contact between the wheels and the ground within the mesh to make sure that it was numerically stable. So there was some work done there to overcome that problem. If we look at the outlook for Phoenix, I don't think Phoenix is going to be taken forward in a continuation of the EXCELLERAT Center of Excellence. I think it was judged from the work that we'd done that it wasn't quite mature enough for GPUs, and there was perhaps a little bit of a lack of expertise within the project to take that forward. But Phoenix itself has been undergoing a transition into Phoenix X, and this was happening during the timescale of the project. So it may well be that it emerges from that as being a very powerful framework for exascale computing. And finally, the sixth code is called CODA. And this is a relatively recently started initiative. It is a partnership between research and industry. It's been designed with specific requirements for exascale, so they're looking at multi-level parallelization and these kinds of technology. So unlike many of the other codes, it's much newer. So the authors have been able to take advantage of new technology perhaps in a different way, at least, to some of the older codes. And the use cases here was basically looking at full equipped aeroplanes. That's really the objective of this code, is being able to do a full airframe simulation. So if we look at the use cases, the common research model. So this has got I think the test mesh that's being talked about here, where we say it's very strong scale, is used to test the strong scaling. Production meshes, I understand, will be very much bigger than that. I think up to 20 times bigger. So the scale of this is really quite challenging. So the work that was done in the project was to integrate a sparse linear system solver from DLR, which was done and then further optimized. There was some test on the numerical stability, testing successfully on GPUs, and nice parallel efficiency with an evaluation on the Joules booster system. Okay, outlook for Exascale. Aim to get Exascale, full entry into service of the code, adapt for new technologies, basically aiming at very, very large simulations with this code. So there's a lot of work, there's a lot of common themes sort of appeared. There's visualization, there's workflow tools, there's simulation, there's new numerical methods incorporated into simulations, there's optimization of existing numerical methods. And I think all in all, those the developments that we're coming up with in all of these use cases are populating this this design cycle, so that we're dealing with the bottlenecks as you go around the cycle, as well as just dealing with them in those particular areas of simulation, post-processing, feedback, and pre-processing. I'll give a plug to the EXCELLERAT success story. So this is a good resource to find out more about the work that's been done within the use cases and the reference applications and across the project as a whole. So if you visit the website that's on that slide, there's a lot of stuff there to see. And I'd like to thank the people named on the slide there for helping me put this together, giving me nice images and those sorts of things.